All right, here is the full summary for section 3.1 where we learn about complex numbers. This is from OpenStax PreCalculus. So complex numbers. Complex numbers arise out of a need to take the square root of negative numbers. I don't like the fact that the square root of -9, for example, is undefined. It's kind of annoying to me. And first of all, note that it is undefined, right? The square root of -9 equals x. What should x be equal to? Well, there's no number, there's no real number that you can put in place for x to make this equation true. Because really what this question is asking you is what number out there, when you square it, gives you -9 as the answer. And there's no answer to that, right? -9 equals x squared. There's no real number solution to this equation right here. 3 squared is +9. Oh, right, but what about -3? Well, -3 squared is also +9. So the square root of -9 would be the number that when you square it gives you -9, but unfortunately 3 doesn't work, -3 doesn't work, so I'm kind of out of options. Well, there's hope. There's hope with these things called complex numbers. In order to answer that question, we define a new symbol. Use the letter I, because why not? And I is equal to the square root of -1. And it turns out that this fact will allow me to do all sorts of stuff. It'll allow me to answer that question that I just posed a minute ago with the square root of -9. But it'll also allow me to do all sorts of other stuff. It'll create this new idea of what a number is that'll be consistent. I can add, subtract, multiply, divide these numbers. I can do all sorts of stuff if I just assume that I, this one new symbol, is equal to the square root of -1. Before I go any further, let me note that this is an equation, so I can screw with it. I can do stuff to both sides of the equation. I can square both sides of the equation. If I squared both sides of the equation, I would get that I squared equals -1. Really, these two equations are saying the same thing. I squared equals -1, or I equals the square root of -1. I like to have them both handy. I like to know both of these facts right here, because in some instances it'll help to think about I this way, and in some instances it'll help to think about I as the thing that when you square it gives you -1. So these will be the two things that will be key to this entire section. So first, complex number. What is a complex number? A complex number is a number written in the form a plus bi. And maybe parenthetically I'll write where a and b are real numbers. And that's all a complex number is. So an example of a complex number would be 2 plus 3i. That's a complex number. Another example of a complex number would be 5. Because 5 can be written in this form. A would be equal to 5 and b would be equal to 0. So 5 is a complex number, as is 2 plus 3i, as is the square root of 7 plus 2/3 I. Those are all complex numbers. Complex number is just a number that can be written in this form. And it'll turn out that if we enlarge what we think of as a number to include complex numbers, we'll be able to do a whole lot of stuff. So first of all, that might seem like a weird idea. Wait, a number is a number. I thought I knew what a number is. And now you're telling me that 3 plus 2i is one number? I know 3 plus 2i feels like a sum of two numbers, but we're going to think about it as a single number, a complex number. It is a complex number, and it's not that strange to enlarge what you think of as numbers. I bet when you first learned numbers, you learned whole numbers, counting numbers, that kind of stuff, and then maybe you added in negatives at some point, and then you added in fractions at some point. Like 3/5 is a number, but if you try to tell my 2-year-old 3/5, he'll get all sorts of confused, because he doesn't think about that as a number. But is it to you? You're not my 3-year-old. You probably understand what 3/5 means, and you don't think about it as a quotient of two numbers. You don't think about it as one number divided by another number. You say 3/5 is itself a number. Similarly, 2 plus 3i, we will not think of as one number plus another number. We'll think about it as a single number, a complex number. So there's a little bit to motivate complex numbers. We need some vocabulary. First of all, a complex number is something that can be written in this form. A is what's called the real part, and B is what's called the imaginary part. And the I is our imaginary unit, which we defined up here to be the square root of -1. That's what a complex number is. So as I mentioned, 5 plus 4i, for example, is a complex number, as is 3 minus 2i, as is -i. Because -i I can think of as 0 plus -1i. These are all complex numbers. It's the first topic. The second topic, complex conjugate. Well, we'll try to change the color I'm dealing with here. Maybe I'll move into red. A complex conjugate, which I'm going to do in red here. Anytime you have a complex number, you can come up with a complex conjugate. And all a complex number is something that can be written in this form. So all a complex conjugate is this guy. So what I'm saying is, if you have a complex number a plus bi, and then you change the sign of the imaginary part, change the sign of b. So if b used to be a positive number, now it's a negative number. If it used to be a negative number, now it's a positive number. If you change the sign of b, you get the complex conjugate. So I can talk about that idea by writing this right here. So the complex conjugate of 5 plus 4i would be 5 minus 4i. Note it's not negative 5 minus 4i. I don't change the sign on a, the real part. I only change the sign on b, the imaginary part. So I get 5 minus 4i. What would be the complex conjugate here? It's already negative. How am I going to do this? All you do is change the sign on the imaginary part. So this currently is 3 plus negative 2i. If I made it 3 minus negative 2i, aka 3 plus 2i, I would have the complex conjugate. And also, if you think about this as 0 minus 1i, its complex conjugate would be 0 plus 1i, which I could write as just I. It's a weird looking I. That'll work. These are the conjugates of these numbers. Why am I bothering with complex conjugates? That's why. What I want to do in just a minute is add, subtract, multiply, and divide these numbers, any complex numbers. If I'm going to understand this new system of numbers, I better understand how to add them and subtract them and multiply them and divide them. And it turns out the key to dividing them will be complex conjugates. Understanding this will be the key to this. So we'll come back to this in just a minute. Before I get into adding, subtracting, multiplying, and dividing, I want to talk a little bit more about complex numbers and how to graph them. How do you graph a number? Well, actually, you can graph a number. You could use a number line. If you had a real number, you could graph it. Here's 0, and here's, I don't know, 1 maybe, and 2. And if I asked you to graph 3/5, you could ballpark it somewhere in here. You could be like, 3/5 is right around in there. Fine. You can graph numbers on a number line. You can graph real numbers on a number line. However, if you're going to graph complex numbers, turns out you can't graph them on a number line. Because we sort of have two different parts. We have the real part and the imaginary part. So I kind of need one axis for the real part and one axis for the imaginary part. What that ends up meaning is that complex numbers, unlike real numbers, are two-dimensional numbers. Real numbers are one-dimensional numbers in that you can always plot them on a number line. Complex numbers are two-dimensional numbers in that if I want to plot a complex number, I'm going to need more than one axis, like I have here. Instead of thinking about them as the x and y axis, I'm going to think about them as the real and the imaginary axes. And it's also worth pointing out that these names are stupid. Like complex just makes you think these things are really hard, and imaginary makes you think they're not useful somehow. That's not at all true. These are as much numbers as anything else is a number. And complex, I don't know. I mean, I guess you can do some hard stuff, but we've seen some pretty hard stuff with real numbers. So don't think about these as complex and imaginary. They're the connotations associated with those words. Don't get too hung up on them. They're just numbers. And those are just the two parts that we're giving names to. Anyways, if I had a number like 3 plus 2i. Actually, I'm not even going to write it there. 3 plus 2i. Its real part is 3 and its imaginary part is 2. So it would make sense to graph it right here. Right, here's where the real is 3, here's where the imaginary is 2. That number should go right here. I can't put 3 plus 2i on a number line, but I could put it on a number grid, a number, I don't know, plane like I have here. 3 plus 2i would go here. Similarly, I don't know, negative 2 plus 4i would be right here. And negative 3i would be right here. And 1 would be right here. Right, 1, you're like, that's not a complex number. I already knew that before I started. Well, complex numbers include real numbers like 1, because 1 can be written in this form, 1 plus 0i. So 1 is in fact a complex number, and it would go right here. Not that interesting. You can kind of think about this as your old number line. But now I have this additional number line so that I can plot all the numbers. Note that they're no longer ordered. Like I don't have this idea of what's bigger or smaller. Is 3 plus 2i bigger or smaller than negative 2 plus 4i? I don't know. What do you mean by bigger and smaller? I mean, the real part's bigger. The imaginary part's smaller. The distance from 0 appears to be a little bit smaller. That's kind of interesting. But they're not ordered like they used to be. Those are just some properties of complex numbers. Note that you can graph them. The next thing, which is really what I focus the majority of this section on, is, all right, I got these numbers, complex numbers, and I'm kind of starting to understand them, although they're still a little bit weird. I should be able to add, subtract, multiply, and divide them. Let's do it. Pick any two complex numbers at random. I don't know, 5 plus 4i, I've used that one already. And I don't know, 3 minus 2i. I'm going to put in some unnecessary parentheses here. And the reason why is I really want to emphasize that this is a single number. I know it looks like two numbers added together, but this is a single number, just like a fraction is a single number. And so I could take this single number and add to it this single number. And what should I get? Well, it would be really nice if this worked out just like, I don't know, algebra has worked out. Like if you saw something like this and you were thinking about the I as a variable, you could add these together. It'd be really nice if complex numbers worked out that way, and in fact they do. Everything that we're going to be doing with complex numbers is going to be treating the I almost like it's a variable. And that's going to be kind of the key to this section. I'm going to say treat I like x. And I'll repeat that a bunch of times, because when I say treat it like x, I mean if this said 5 plus 4x plus 3 minus 2x, you could do that. And it turns out that the method you use to add together these two complex numbers will be identical to that. So if you were adding those together, I don't know, maybe you would say, well, this would be 5 plus 4. I could combine like terms. If these were all x's, you would view this as two different terms, and this is two different terms, and you'd combine like terms. You'd take the 5 and the 3, and you'd add them up. And then you'd say, I got 4i and negative 2i, and those net out to positive 2i. It'd be nice if things worked out that way, and in fact they do. When you're adding complex numbers, all you got to think is treat the i's like the x's. That's it. What about subtracting? I'm going to put a slash here because they're so similar. Wouldn't it be nice if 5 plus 4i minus 3 minus 2i, I could treat the i's just like the x's? Well, in fact, you can. Note that this time the parentheses are important. Over here, the parentheses didn't do anything. It just made me think of this more as one number. Over here, it's important. If I don't have the parentheses, I'm only subtracting the 3. But this is all one number, so if I'm going to subtract two complex numbers, I want to subtract this entire thing. I need the parentheses. But it'd be nice if we could just treat these numbers as though the i's were variables. If they were, I guess my first step would be to get rid of the parentheses by taking this negative 1 and distributing it through. That would give me negative 3 plus 2i. And then combining like terms. You can write the order differently if that helps, or you can just look at this and say 5 minus 3 is 2, and 4i plus 2i is 6i. And in fact, it's exactly what you do. When you're subtracting complex numbers or adding complex numbers, all you got to do is treat the i's like the x's. Cool. What about multiplying complex numbers? Well, good news and bad news. Bad news is it's a little bit harder than this, but good news is we're still going to take advantage of this, treat the I like the X. So let's multiply complex numbers. I'm getting lazy as this video goes on. Pick any two complex numbers you want. I'm going to go ahead and pick on the same ones just for consistency, although it really doesn't matter which ones you choose. But suppose I wanted to multiply 5 plus 4i times 3 minus 2i. Wouldn't it be nice if I could treat this just like I was multiplying two binomials? You can. 5 times 3 is 15. I'd FOIL this if they were binomials, right? 5 times negative 2i, negative 10i. 4i times 3i is 12i. And 4i times negative 2i. Well, if it were 4x times negative 2x, you take the 4 and the negative 2, the coefficients, and get negative 8. And then you'd say I times I, or x times x, is x squared. It'd be nice if you could do this. In fact, you can. But wait a minute, I got a problem. I can combine like terms to get 15 plus 2i minus 8i squared. But how can that be my answer? I'm multiplying together two complex numbers. Over here, when I added two complex numbers, my answer was a complex number. When I subtracted two complex numbers, my answer was a complex number. But when I multiply two complex numbers, I get this mess right here, and this doesn't look like a complex number. Looks pretty complex to me, true, but recall, complex numbers have to be written in this form. And this is not in that form. This is a plus bi plus ci squared. It's not a plus bi, but there's hope. I can get rid of the I squared. Not just get rid of it, but take advantage of the fact that I squared equals -1. Remember this. Remember, this is our definition of I. It's the thing that when you square it gives you -1. So because I squared is -1, I can come down here, and in place of I squared, I can write -1. But of course, -8 times -1 is just +8. I shouldn't say of course, that's like condescending. This would be equal to this, and now I can combine like terms and say 15 plus 8 is 23 plus 2i. And note that I now have a complex number. I could see somebody getting here and saying, oh, this is 2i plus 23. Yes, that's true, but you don't want to leave your answer like this. You want to write it like this because this is not a complex number. It's damn close to a complex number, but it's not a plus bi. It's bi plus a. You want it in this form so it looks like a complex number. Let's get rid of that. We're 3/4 of the way through the main concept from this section: adding, subtracting, multiplying, and dividing complex numbers. Unfortunately, dividing is probably the most challenging. But the good news is that really all it relies upon are things we've already done. If you can multiply complex numbers, which we just did, and you can find the complex conjugate of a complex number, find the conjugate of a complex number might be a more succinct way to say that. You can divide complex numbers. So let's say for some reason I wanted to know what is 5 plus 4i divided by 3 minus 2i. And I'm sure using these complex numbers is getting a little bit tired, but whatever. I chose them, I'm sticking with them. Suppose you wanted to do that. Well, first of all, division, you might not have thought to write it like this. You might have written the weird little division sign in between the two. But what I'm going to tell you to do is anytime you're dividing complex numbers, write them as a fraction. Write them like this. It'd be nice if I could just say this is 5/3 minus 2i or something, you know, divide the 4 and the 2. But algebraically, that doesn't work out. Just like if these were x's, you couldn't cancel the 4 and the 2 because you can't cancel over addition and subtraction. You can only cancel over multiplication. For that same reason, I can't just go canceling things out. But what I can do is take advantage of a nice property of a fraction that allows me, anytime I have a fraction, I can multiply the top and the bottom of that fraction by a number without changing the value of that fraction. That's the reason that 1/2 is equal to 50/100ths. Right? These two things are the same. The reason why is all I did is I took this fraction and I multiplied the top and the bottom by 50. And since I multiplied the top and the bottom by the same number, I didn't change the value of this fraction over here. I'm going to do that same thing here. Except I'm not going to multiply the top and the bottom by 50. What I'm going to do is I'm going to multiply the top and the bottom by the complex conjugate of the bottom. Anytime you're dividing complex numbers, the way you do it is you multiply by the complex conjugate of the denominator in the numerator and the denominator. You have to do it to the top and the bottom so you don't change the value of the thing in red. But by picking the complex conjugate, a nice thing will happen down on the bottom. And what do you mean nice? What do I mean nice? Well, it turns out that any number times its complex conjugate is a real number. Somehow, through the magic of complex numbers, when I FOIL out the denominator here, I will end up with no i's at all. That is why the conjugate is so important. Is it gives me a complex number. For any given complex number, it gives me another complex number that I can multiply it by that leaves me with the real number. No i's left behind at all. Let me show you how that works. If I were multiplying these together, note that when you're multiplying fractions, maybe I'll write it down here, you just multiply straight across. So really what I have are two different multiplication of complex numbers problems. I first got to figure out what's 5 plus 4i times 3 plus 2i, damn near what I did here. Then I got to figure out what's 3 minus 2i times 3 plus 2i. And both of those should be complex numbers because when I multiply together two complex numbers, I get a complex number. But the complex number on the bottom will be a nice complex number in that it won't have any i's. Let me show you. 5 times 3 is 15. I'm foiling out the numerator here. 5 times 2i is 10i. 4i times 3 is 12i. And 4i times 2i is 8i squared. Down in the denominator, 3 times 3 is 9. 3 times 2i is 6i. Negative 2i times 3 is negative 6i. Hey, how convenient. I got a plus 6i and a minus 6i. Was that a special thing that happened in this problem? Nope. That happens anytime you multiply by a complex conjugate. That'll always happen when you multiply two things of this form, is this term and this term will cancel each other out. I got the negative 2i and a positive 2i, so a negative times a positive is a negative, and 2i times 2i is 4i squared. This might not look too pretty, but I can clean it up quite a bit. 8i squared, like I did over here, is really 8 times negative 1, so this is negative 8. So I have positive 15 and negative 8, that nets out to positive 7. And 10i and 12 more I, that gives me 22i. Down in the bottom, the 6i and the negative 6i cancel out. Negative 4i squared is negative 4 times negative 1, which is positive 4. So this whole thing is positive 4, and when I add 9 to positive 4, I get 13. Get here. This is fantastic, because now I don't have a complex number divided by a complex number. I have a complex number divided by a real number. And you could nitpick there. You could say, well, real numbers technically are complex numbers, but you know what I mean. There's no i's hanging out here. And that's a really good thing, because my goal is to get a complex number, a plus bi. And a plus bi does not have any i's in the denominator. The only I up here is being multiplied by the imaginary part. This is not done because it's not an a plus bi form. But if you're real good with algebra, you might recognize that this is 7/13 plus 22/13 I. This is in a plus bi form. Why is that true? Well, I guess 22/13 I is the same as 22i over 13. That's because when you're multiplying a fraction times a number, you can think about that number as I over 1 and then multiply straight across. So this is 22i over 13. And now I have two fractions that have the same denominator, so I just add up the numerators. That gives me this. It's easier to justify going backwards, but if this is the same as this, then this is the same as this. This right here is my answer, and this will work anytime you're dividing complex numbers. You can always divide complex numbers by multiplying the top and the bottom, the numerator and the denominator, by the complex conjugate of the denominator, and then simplify like this. These four examples I consider the main topic from this section, but one more thing I want to talk about is powers of I. When you multiply I by itself, some interesting things happen. I don't know where the hell I'm going to do this. I guess right here, maybe. Here, maybe. Here, maybe. Okay, let's go down here. I to the first power just means I times itself one time, just I. That's not that interesting. I to the second power would be I times I. But wait a minute, I times I already figured that out. I to the second power, I know that I to the second power is negative 1, almost by definition. That's how I'm defining I, as I say I squared is negative I. So I get a negative I right here. What about I to the third power? Well, I to the third power would be I times I times I. What's I times I times I? Well, that's kind of a hard question. But when I'm multiplying together things like this, because of the associative property, I can multiply the first two together. I can say I times I, get that answer, and then multiply it by this third I here. This I times this I is I squared, and as I figured out above, I squared is negative I. Sorry, that's wrong. It's negative 1. Careful there. I squared equals negative 1. So down here, I squared should have been equal to negative 1. So when I multiply this I times this I, I get negative 1. And then I have to multiply that by the third I. So what is negative 1 times I? Well, if I could just treat the I like a variable, negative 1 times x is negative x. And you can. So this is just negative I. So look at what's happening here. I to the first power is I to the second power is negative 1. I to the third power is negative I. What the hell pattern is going on here? Well, you can see the pattern when you go to the next step, I to the fourth power. I to the fourth power would be I times I times I times I. And I'm going to figure that out maybe a little bit clever by first multiplying these two i's together. I times I is I squared, which I already figured out was negative 1. Maybe I shouldn't underline it. It'll look like a fraction. And then multiply these two i's together. Maybe this should be color-coded. Maybe that would help. Let's make these in red. Or purple, I guess, if they're like blue and red. These two i's multiplied together give me negative 1. So I got negative 1 times negative 1. What's negative 1 times negative 1? Isn't that positive 1? Yep, sure is. So I to the 4th power is positive 1. Wait, but that's kind of interesting. So where do things go from here? What's I to the 5th power? Well, I to the 5th power is just I to the 4th power times another I. And I to the 4th power I just figured out is 1, and multiplying by 1 is really easy. 1 times I is just I. And similarly, I to the 6th power is I to the 4th power times I to the 2nd power. And the reason I chose to break it up like this is I to the 4th power is so nice. I to the 4th power we figured out is just 1, and multiplying by 1 is easy. I squared is negative 1. 1 times negative 1 is negative 1. In fact, what ends up happening is we get in this little loop. That I to the 1st power is I squared is negative 1, I to the 3rd power is negative I, and I to the 4th power is 1. So we kind of get this little loop that we can go around every time we multiply by another I. And I guess what you can do, one application of this, what your book will get into, is it'll ask you a question like, what is I to the, I don't know, 102nd power? Man, I don't know. That seems like a whole lot of going through argument. 102, that's a whole lot of I's to write out. That seems like a lot of work. Well, note that this is just, I to the 4th power is just a 1. And this is a whole bunch of groups of 4. In fact, this is 25 groups of I to the 4th power. I to the 4th power to the 25th power. I to the 4th times I to the 4th times I to the 4th times I to the 4th. 25 times is I to the 100th power. But wait, you don't have I to the 100th power. You have I to the 102nd power. Okay, so then tack on 2 more of them. This is equal to this. It's a weird way to write this, but it's equal to this. Note, this is an I. This isn't like a 0.4 in the exponent. The problem with I's is they're kind of hard to write when you get some exponents going around here. I to the 4th to the 25th times I squared. This is 100 of the I's. These are the remaining 2. So what is I to the 102nd power? Well, this would just be 1 to the 25th power times I squared is negative 1. But 1 to the 25th power, isn't that just 1? Yup, sure is. And 1 times negative 1, isn't that just negative 1? Sure is. So I to the 102nd power is negative 1. More generally speaking, you can cancel out groups of 4. As many groups of 4 as you want. So if you have I to the 379th power, for example, this is a whole bunch of groups of 4. How many groups of 4? Frankly, I'm not sure. But I can take 4 and divide it into 379. 4 goes into 37 9 times. 9 times 4 is 36. Subtract. You got 19. 4 goes into 19 4 times because 4 times 4 is 16. And you got 3 left over. So what I'm saying is I to the 379th power is really just I to the 4th 94 times with 3 more I's left over. 4 times 94 would give me 376. I know that because when I did 4 divided by 379, I got 94 with 3 left over. So I get here, this whole thing, it's ugly looking, but you don't got to worry about it. This is 1 to the 94th power, which is just 1. So 1 times I cubed, well, I figured out I cubed either from this little cycle picture or from over here is negative I. So I to the 379th power would just be negative I. I think that's everything I have from this section, so I'll stop this video here.